Lesson 2 of Chapter 11 is on probability. First, before we do this, I've got two columns, and the first column represents experiments, and the second column represents outcomes. If we match the experiments with the outcomes, the first experiment says tossing a coin. Obviously that one matches to this because you have two different outcomes, heads and tails. We have rolling a six-sided number cube, and you have six different outcomes, 1, 2, 3, 4, 5, and 6. And the last experiment is drawing a ball at random from a box holding one green, one red, and one blue would give you three different outcomes, green, red, or blue. This leads us into probability. So if you look right here, this is our definition of probability. You take the number of times the event occurs and you divide by the number of trials. We're specifically going to talk about theoretic probability. And the definition of theoretic probability is here. The theoretic probability of an event is the ratio of the number of ways the event can occur to the total number of equally likely outcomes in the sample space. An example, a student rolls a six-sided number cube. The theoretic probability that the student rolls an even number is 3 over 6 because there's three different ways to roll an even number and there's 6 possible outcomes. So some vocabulary, we're saying true or false in this. It says theoretic probability is the sum of the numbers of ways an event can occur and the number of possible outcomes. This would be a false statement. A true statement would be the ratio of the number of ways for an event to occur to the total number of possible outcomes is the theoretic probability. On to problem number 1, finding the experimental probability. It says a softball player got a hit in 20 of her last 50 times at bat. What is the experimental probability that she will get a hit in her next at bat? Well, if we use the words in the box at the right to complete the ratio, to find the probability of getting a hit, we take the number of hits and we would divide by the number of times at bat. So this would give us 20 over 50, which gives us as a decimal 0.4. As a percentage, it gives us 40%. On to problem number 3, finding theoretical probabilities. It says, what is the theoretic probability of getting a sum that is an odd number on one roll of two fair number cubes? Well, I've got a chart on the right. So you can see that if you roll a 1 and a 1, it gives you an outcome of a 2. If you roll 3 and a 4, it gives you an outcome of a 7. So hopefully you understand this chart and how it's working. So let me erase those marks. And problem number 4 says the table shows the possible sums for one roll of two number cubes. Circle the favorable outcomes. Well, since we're trying to get an odd number, we could get 3, we could get 5, we could get 7, we could get 9, or we could get an 11. So there's all of our odd outcomes. I just circled 18 favorable outcomes, and there's 36 total outcomes. So 18 divided by 36 reduces into 1/2, or 50%. Problem 4 is finding probabilities using combinations, combinatorics. Problem says, what is the theoretic probability of being dealt all 4 sevens in a 5-card hand? So kind of like poker. So we're going to complete this chart to help us. First, we find the number of combinations of 4 sevens from 4 sevens. So that would be 4 NCR4 like you can see here. And so I'll put a 4 there, and this would end up giving us one outcome. There's one way to get 4 sevens from 4 sevens. Makes sense, doesn't it? Next, we go on to do the number of combinations of getting one non-7 card from the 48 remaining. So we're doing 48 NCR1. And so fill in with ones there. That gives us a 47 factorial on the bottom. This would give us 47 different outcomes. Sorry, 48 different outcomes. 48 different ways to get a card that's not a 7. So now we have to multiply these. So 4 NCR4 times a 48 NCR1 would end up giving us 1 times 48, which is just 48. So keeping that in mind, now we go on to number 8. It says find the total number of possible 5-card hands. So to do that, we have to do a 52 NCR5, which would be calculated out, which would give us a number, let's see here, if we fill these in, 5 factorial times 47 factorial on the bottom, which gives us 2,598,960. Again, the way we're doing that is just using the calculator, doing 52 math NCR 5, and it calculates it for us. So there's that number. Now if you go to number 9, it says use your answers in exercise 7 and 8 to write the probability. So the probability of a hand with 4 7s is the 5-card hands with 4 7s divided by the possible 5-card hands. So to simplify that, we'd have 48 over the 2,598,960, which would simplify into 1 over 54,154. If you wanted that as a decimal, it would be 0.0000184 0.1846. So it's not very likely that you get 4 7s when you're being dealt a hand of 5 cards. One important piece to this example is we're using NCR versus NPR, because when you're dealt cards, the order of which you're dealt them does not matter. So order is not important. Going on to problem number 5, it says suppose a batter's strike zone is 15 inches by 20 inches, and its high inside strike zone is 3 inches by 5 inches. What is the probability that a baseball thrown at random within the strike zone will be a high strike zone? So the first thing we do is we find the area's batting strike zone. So it's 15 by 20, which gives us 300 square inches. The next thing we're going to do is find the area of the batter's high inside strike zone. So that's 3 times 5, which is 15 square inches. Now what we'll need to do to find the probability of getting a high inside strike is we'll take the area of the high inside strike zone divided by the area of the total strike zone. So that would give us 15 over 300, which simplifies into about 0.05, or roughly 5%. The last question then says the probability that a baseball thrown at random within the strike zone will be a high inside strike is about 5%. So then, the last question says find the probability of getting a 3 when rolling a fair number cube. So we'll have to have the number of ways you can roll a 3, which is only one way, over the total possible outcomes, which is 6 outcomes. And so your answer would be 1 over 6. Second question, find the probability of getting a 2 or a 4 when rolling a fair number cube. So we have the number of ways of rolling a 2 or a 4. Well, there's 2 possible favorable outcomes. There's 6 total outcomes. That reduces into 1/3 or 33.3%. On to the next page. We're going to do a simulation, and we're going to talk about why a simulation is better the more times you perform it. So number 17 says using your graphing calculator, enter random integer 1, 2, and 5. So on your calculator, if you go math and then go over to probability, go down to random integer, and we do so if you do random integer and we're going to use a 1 and a 2, and we're going to get 5 outcomes. If we do this, it gives us random integers. So I got 2, 2, 1, 1, 2. If we repeat this experiment, but doing it for 10 outcomes and then also 20 outcomes, so I'm going to do it for 10 outcomes here, and we get 2, 2, 1, 2, 2. Then we get 1, 2, 1, 2, 2. Okay, I'm going to do this one more time. This time we're going to do it for 20 times, not just 10, but 20. And we get 2, 2, 2, 1, 2. 2, 1, 2. Then we got 1, 1, 1, 1, 1. So 5 straight ones. I'm going to have to use my right arrow here now. To get my last one. So let's work backwards here. 2, 1, 2, 2, 1. And we got 1, 1, 1, 2, 2. So there's our experiment. We just conducted our experiment with our calculator. Now number 19 says find the experimental probability of landing on heads for each of the experiments above. So when we did it 5 times, how many times did we get a head? So we're letting 1 represent heads, so we got 2 out of 5, which is 0.4. When we did 10 trials, we got 1, 2, 3, so 3 out of 10, which is 0.3. And when we did it 20 times, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 20, which is 0.55. So the question out at the bottom says, explain why a simulation is better the more times you perform it. And the answer is, the more times you perform it, the closer the experimental probability gets to the theoretic probability. So you can see here that when I did 5 trials, 0.4 is pretty close. When I did 10 trials, 0.3 is not as close. But when I did 20 trials, I was the closest. I should get 50% of the time. So to finish up with, just to evaluate, check off the vocabulary words that you understand between experimental probability, simulation, and theoretic probability, and then rate how well you can determine the probability of events.